Now we look at the fourth question. The question is, consider the ring C01 with the operation of pointwise addition and pointwise multiplication. Give an example of an ideal in this ring which is not maximal ideal. Now, if R is a ring and M is an ideal of R, so when M is maximal, if M is maximal, then there exists another ideal U such that M subset of U subset of R, where either M equal to U or U equal to R. So M is maximal if this one of this condition is held. Now we take S equal to F belongs to the C of 0 1. Continuous function over 0 1 is a ring, you know that, and F of 0 and F of some other point in this ring, say 1 2 equal to 0, and this is not an maximal ideal, is not maximal because there exists another ideal U F of 0 equal to 0, and S is properly contained in this ideal, properly subset in this ideal, and U is a proper subset of C of 0 1. So this condition is not hold for this case. So S equal to F belongs to C of 0 1 such that F of 0 equal to F of 1 equal to 0 is not maximal ideal, but this is a maximal ideal. You prove it yourself. But S is not maximal ideal because S belongs to this ideal. Now the next question is, compute the multiplicative inverse of 4x plus c in the field z11x quotient x square plus 1. Now, how this field looks like? Zx quotient x square plus 1 is equal to, and this field looks like fx plus x square plus 1, where fx belongs to z11x. Now z11x is an field and 1 being an unity of this, so 1 plus x square plus 1 being an unity in this ring z11x quotient x square plus 1. Now each element in this field looks like ax plus b plus x square plus 1. Each element of this field looks like that, where ABR belongs to 11, Z11. Actually, this is class A bar, B bar. Now, we usually read it AB belongs to Z11. Now, the question is the multiplicative inverse of this. So actually this equal to, actually 4x plus 3 can be written as 4x plus 3 plus x square plus 1. Here 4x plus 3 plus 0 into x square plus x, because this can be written as ax plus b plus gx plus x square plus 1, where gx belongs to z11x. And so generally we read this as ax plus b and this as 4x plus b. Now these two equal to 1 plus this. These two equal to 1 plus this. So actually these two, actually if we multiply this and this, then we get that if I call it x, if I x square plus 1 call it I, so ax plus b I into 4x plus 3 I. So by the multiplication of quotient, this became ax plus b 4x plus 3 plus I. So here we add this I equal to 1 plus this equal to I. So actually ax plus b into 4x plus 3 equal to 1 plus some gx into x square plus 1. So this became 4a x plus, 4a x square plus 4bx plus 3ax plus 3b, and this is equal to 1 plus some gx into x square plus 1. Here in this case we take it in the right side and write it in gx x square plus 1. So this equal to this, and this equal to 4a x square plus 3b and 4b plus 3a x, and this equal to 1 plus gx x square plus 1. So actually this become 4x square plus 3b minus 1 plus 4b plus 3ax equal to gx into x square plus 1. Now look at, this is not in the right hand side, so we put here 0, so 4b plus 3a equal to 0, where modulo 11, because these b and a are z11, and here 4a, here 4a plus here 4a equal to 3b minus 1, because if these are two equal, if this and this equal, so we read it x square plus, we read here if these are two equal, from this we read it 4x square plus 3b minus 1 equal to some, suppose 4a x square plus 1, and this two sides are equal, so here we actually equate these two sides, modulo 11. Now if we take a equal to 6 and b equal to 1, so the both condition, this and this are satisfied. So our multiplicative inverse of 4x plus 3 became 6x plus 1. So the multiplicative inverse of 4x plus 3 is 6x plus 1. And if you check it yourself that 4x plus 3 into 6x plus 1 plus this equal to 24x square plus 18x plus 4x plus 3 plus of x square plus 1, and this became 2x square. Why 2? Because 11 into 2 equal to 22, so 22x square plus 2x square equal to 2x square, and this is equal to 22, so 0 plus 3 plus x square plus 1, so 2 into x square plus 1 plus 1 plus x square plus 1, so this can be read as x square plus 1. So the multiplicative inverse of this equal to this, so 6x plus 1 is the answer. Now the next question is which of the following statements are true? Let a equal to m3r be such that a to the power 4 equal to I and n not equal to plus minus I, then a square equal to I. First of all, we read a to the power 4 equal to I, then x to the power 4 equal to 1. Why x to the power 4 equal to 1? Because if a to the power 4 equal to I is satisfied, then x to the power 4 equal to 1 be an equation of variable x. From this we read it, and this is necessarily not characteristic equation or minimal equation. This is an equation. If this satisfies, so from this we read it, and this implies x to the power 4 minus 1 equal to 0. So x to the power 4, and this can be written as x minus 1 plus x square plus a plus 1 equal to 0. Since the condition is a plus not equal to I, so this 2 is not minimal polynomial together. So the minimal polynomial of a is either x plus 1 into x square plus x plus 1 or x minus 1 into x square x plus 1. So this equal to 0 or this equal to 0. So this is not necessarily 2. So this is false, wrong option. Now we check the second option. A q equal to I, and this can be written as x q equal to 1, and this can be written as x q minus 1 equal to 0, and this can be written as x square plus x plus 1, and the condition is a not equal to plus minus I. So from this, the minimal polynomial of a is x square plus x plus 1, because x minus 1 is not minimal, because x minus 1 is minimal and every matrix satisfies its minimal polynomial. If x minus 1 is minimal polynomial, then this equal to 0, and every matrix satisfied its minimal polynomial, so a equal to I, and this contradict the conditions, so this cannot be minimal polynomial. So x square plus x plus 1 equal to 0 is a minimal polynomial, and from this we read a square plus a plus I equal to 0, since every matrix satisfied its minimal polynomial. Here x minus 1 into x square plus x plus 1 is not minimal polynomial of the matrix A because A is a 2 cross 2 matrix. So they cannot satisfy 3 cross 3 degree equation. So this is not a minimal polynomial. This cannot be minimal polynomial. So the right option is B. Now for similar equation aq equal to I equal imply this and this equal to I. Here minimal poly minimal polynomial is either x minus 1 into x square plus x plus 1 or x square plus x plus 1. Because this is a 3 cross 3 matrix, so this can be a minimal polynomial of A or this. But when A is 2 cross 2 matrix, so this cannot be minimal polynomial of A. So this must be for the previous case, and since this matrix is 3 cross 3 matrix, so either this is a minimal polynomial or this is a minimal polynomial. If this is a minimal polynomial, so x square plus x plus 1 equal to 0, and in that case the option C is not true. So the right option is B. Now the next problem is, find an orthogonal matrix P and a diagonal matrix D both in M2R such that P transpose AP equal to D, where A equal to this. First of all, we find the eigenvalue of this matrix. The characteristic equation